So for our next concept with regards to isotopes, I'd like to revisit this slide that was used 2 videos ago when defining isotopes. So we said isotopes for a particular element. Those are species that they have the same number of protons or same atomic number, but they have different masses or different numbers of neutrons. We gave the example of carbon, at least in this table. So carbon actually comes in 4 different flavors. Some carbon in the atmosphere or in the, in a sample is naturally occurring, has an atomic mass of 11 AMUs, some 12, some 13, and some 14. Depending upon what element you are talking about, depends on how much of that particular isotope is present. You may say, okay, that's all well and good. But Mrs. Lapola, when I look at the periodic table and I know that atomic masses for a particular element are on the periodic table, when I look at carbon, there's only 1 square on the periodic table for carbon and only 1 atomic mass listed. But yet, according to what is shown here in this table, I have 4 different isotopes. They have 4 different atomic masses. How come on the periodic table there's only 1 atomic mass listed for carbon? And not only that, it's a decimal. It's 12.01, not just 12. What is it? What's the deal with that? That speaks to the concept of average atomic mass. So the masses that you see, the atomic masses that are published on the periodic table for an element are actually a weighted average of that element's individual isotope. So the atomic mass that is published takes into account how prevalent each particular isotope is for that element. Let me go back to this table, but according to this table, it says that almost all the carbon found in nature is carbon flavor C12, so it has an atomic mass of 12. And that's reflected is what you see on the periodic table as carbon having a mass of 12.01. It's not exactly 12. Carbon 11, 13, and 14 contribute a little bit, but the vast majority of it is carbon 12. So we can calculate what the atomic mass is for a particular element by using a weighted average. And so to calculate the weighted average for an element, it's a little bit different than a regular average. When you think about average, you think about add up the numbers you have and divide by the total numbers you have. In a weighted average, we take into account the percent abundance of each isotope. We take that abundance, divide by 100, and multiply it by the mass of the corresponding isotope, and then add them all together. So for example, in this question that we're going to work in the next slide, let's say we have a particular element that has 2 isotopes. So 2 different flavors. Same element, but 2 different flavors of it. First isotope has a mass of 113 AMU with a percent abundance of 4.28. Second isotope has a mass of 115, percent abundance of 95.7. And I want to know what the atomic weight of that element is, or the same thing as the atomic mass. And so to calculate that, we're going to use this equation, which is that the atomic mass is equal to the sum of the abundance of each isotope in decimal form multiplied by its corresponding mass. So in this, I've got the same question up here. And so I can set up my equation to say that the atomic weight of the element is equal to the mass of each isotope. So I have the mass of my first isotope and of my second isotope. Each mass is multiplied by its abundance, but in decimal form. So I take the percent and divide by 100. So that gives me the numbers in parentheses. When I go ahead and put those in my calculator, this is the two terms that come up. And I'm not going to be particularly picky with significant figures for this particular problem, but just to kind of belabor the point, if I wanted you to answer this with proper sig figs, I would say, but just to belabor the point, let me get my pointer here. Just to belabor the point, when you multiply, remember we care about total number of sig figs. So the 4.83, that would be significant. This also has 3 sig figs, so the 110 would be significant. Then when I add, I care about number of sig figs after the decimal. Well, this has 2, this has none. So this is what comes out of your calculator. But if I asked you to report this to the proper number of sig figs, you would, since we're adding, you would report an answer with no digits after the decimal. So it would just be 115 or 115 AMUs. And that makes sense, right? Because the vast majority of the isotope for this element was 115 versus 113. Okay. So there's one example on your recitation worksheet. There are 2 problems, at least 2 problems on your MindTap homework. Given information about a species' isotope mass and percent abundance, you should be able to calculate its corresponding average atomic weight or average atomic mass.